Good morning. So today we will begin studying the line integrals, the first type of integrals over, the first type of line integrals in this chapter. There are in fact two types of integrals, and you will see that when we move to surface integrals, which is the last type of integral, you're going to have the same type of framework. Line integrals are integrals where the function to integrate, the function is evaluated on a curve. So really it's the complete analogy of the, at least for one of them, it's the analogy from the Riemann integral, except the domain is not a straight segment, but it's a curve. And we'll talk about the motivation for it, but the reason there are two types of integrals that we will study side by side is because the function to integrate can be a function of several variables, sometimes called a vector, a scalar field. To again emphasize the difference between the function of several variables in which the value of the function is a real number, as opposed to a vector field when the function, of course, is a vector, the value of the function is a vector. The meaning of these integrals is different, okay? They're not replaceable. I mean, they serve different purposes, basically. Although there are some connections, as you'll see, which is the reason they are taught together. But just to keep in mind, there are essentially two types of integrals we will define, both of them called line integrals. But depending on the function to integrate, we're talking about a line integral over a scalar field versus the line integral over a vector field. So let's start with a little motivation here before we get into the main topic. And by this point, I hope you realize that you shouldn't go too fast over this topic. Don't rush to the computational part of it, because it's very important to understand the motivation behind these tools, how it is defined, and then save it for later how you compute it. Because if you understand the first part, the computational aspects are actually very simple. Many people have troubles toward the end of the class. Because there are so many concepts coming together here at the end. Just focus on understanding the concept and how you actually set it up. And then the actual computation is going to come easier once you do the first part correctly. So we're not going to get into all the details of how to construct the Riemann sum, because we did it before in details with double integral, triple integral, and so on. But the concept is the same. You're going to split the domain in non-overlapping equal parts, pick an intermediate point, evaluate the function of that intermediate point, come up with a sum, take the limit, and if that limit exists, there's your integral. Well, let's talk about a little bit of a motivation here. So as an example, which resembles actually the center of mass chapter or section with the line integral. Let's say the object, let's say you have an object which is in the shape of a wire, a thin wire, meaning that the only meaningful dimension is the length of that wire. And let's say that wire is in 3D or 2 dimensions. The integral is the same whether you define it in 3D or 2D. Just like for a thin plate, it makes sense to define the density as the mass over the area, so in terms of kilograms per square meters. It may make more sense for this object, this heavy wire, let's say, to define the density of it, let's call it f of xyz, as a ratio between unit of mass at that point, xyz, over unit of length. So you can define the density of the wire, of course, assuming that the mass is not constant, because if it's constant, you don't need any integral. It's in terms of units of mass over length, like as in, kilograms per meter. So then how would you compute, for example, the total mass? Well, the total mass, at least the mass, of course, at this point, if the piece of the wire is very, very small, okay, so if you imagine the wire here and you cut it into small pieces, and you look at a very small piece, then the mass of that piece, again, which is essentially defined at that point, xyz, is going to be the density given by this function times the length of that piece. And by the way, to come up with these notations here, traditional for the arc length, which you probably know already from the other applications, the notation ds, little s, is the typical notation for the arc length so the notation for the arc length near a point. So basically an arc length whose length basically, for a very small arc length as you partition the wire, right, in the Riemann sum. It's the equivalent of dx, right? The equivalent of dx, right, in the integral of a function from calculus 1, like the integral from a to b of f of x dx. So keep this in mind that we have this notation. So in other words, if we come up with an integral in which we evaluate the function over a curve instead of a straight segment like this, then we can come up, of course, with the total mass, right? So if we define this an integral over this quantity, right? So an integral over this will result in computation of the total mass of the wire. Again, this is just like an example which is analogous to the what we learned with the center of mass of a thin plate. In that case, the thin plate had a density in terms of units of area, units of mass over the area. Double integral over a density defined this way at all points would result in the computation of the total mass. And then you can extend this to compute the center of mass of the plate, and analogously here the total mass of the wire. So let's see how it is defined more formally, these line integrals. So the first type again is the line integral of a scalar field. And let's write it in terms of f of x, y, z. Again, if it's in 2D, it's the same same definition. Line integral of a scalar field over the curve or line, in the sense of a curve here, c given by r of t equals the vector function x of t, y of t, z of t. So the curve over which we integrate the scalar field is defined with a vector function with t between a and b, the parameter domain. So roughly speaking, basically, if you have that wire, let's say you have this wire like this, initial point corresponds to t equals a, final point to t equals b. And again, we've split this into non-overlapping pieces. And let's say this is a typical split or piece of the wire. And ds is the arc length of it. So how do we construct the integral? Like with all integrals we learned so far, right? We're going to pick an intermediate point. Let's call that intermediate point xi star, yi star, zi star. That's a typical notation because remember that results from splitting the parameter domain into the partition t naught, t1, ti minus 1, ti, and so on up to tn. And then you're going to pick an intermediate parameter domain, an intermediate point on the domain, let's say ti star. And when you evaluate that point on the, or you plug it into the curve itself, that results into an intermediate point on the curve itself. Okay, so the Riemann sum, therefore, is going to be the summation with the function evaluated at this intermediate point, xi star, yi star, zi star, multiplied by the arc length. So again, let's focus for a moment before we talk about how we can compute it. Domain of integration is a curve. The curve is always given in the parameterization form, right, as a vector function with the domain, parameter domain between A and B. Split that curve into small non-overlapping pieces, pick intermediate points on each piece, evaluate the function at each intermediate point, multiply it by the arc length, sum up these quantities, you obtain a Riemann sum, take the limit of the Riemann sum as n goes to infinity. If the limit exists, it will approach a finite limit, which will formally denoted by the integral over C f of x, y, z ds. So this is the formal notation of a line integral over scalar fields. Again, let's not confuse the formal notation with the way to compute it, which I'll explain in a moment here before we move on to actual examples. So on the left side again, let's write down again the formal notation, the integral over C, C again denoting the curve, function evaluated at the point on the curve, ds. So the integral over C of f ds, this should be actually a small s. It's like, you can also write it like this, ds if you prefer. I kind of like to make capital S but smaller, and then I'm gonna make it much bigger when I need a big S, which is gonna be the case actually later when we move on to surface integrals. So anyway, in this context, ds represents the arc length. How do you compute it? Well, as you already can see here, I'm alluding it here on the left side, to make this partition on the curve, basically this results from a partition on the parameter domain, right, from A to B. So eventually, when you plug in the actual point on the curve into the function f, everything ends up being a function of the parameter t. So the way to compute the line integral is via an old-fashioned Riemann integral of calculus 1. From A to B, the parameter domain, the function evaluated at the point on the curve, so that means you pick the components on the curve and plug them into the function, so f of x of t, y of t, z of t. Times ds. Now remember the arc length, remember from earlier topics, the arc length is nothing but the magnitude of the tangent at that point, magnitude of arc prime of t. So square root of x prime of t squared plus y prime of t squared plus z prime of t squared dt. We're going to write again the formula on the next page, but it boils down essentially to computing this calculus 1 Riemann integrals, right? Evaluation of the function at the point on the curve multiplied by the arc length of that small piece, which is nothing but the magnitude of the tangent vector, and then that results in a function of t, and then you integrate this over the parameter domain AB. There are other shortcut notations of this, which I'm going to mention on the next page, which are important to keep in mind because it'll make the formula sheet easier to write. So let's move on to the next page. Okay, so let's write down again the formal notation and the way to compute it in red here. Formal notation, we mentioned it before. We can write in a more compact way the way we compute it by writing it this way. So the integral from A to B, f of r bar of t. So this simply indicates that you plug in the curve into the function f times the magnitude of r prime of t dt. You can leave it like that if you know what we're talking about here, what r prime of course is, and f of r of t, or if you prefer, you can write it in a more expanded form like before. f of x of t, y of t, z of t. It shouldn't be necessary though, because it kind of makes a mess in the formula sheet and even here on my notation here. So this is x of t. And then times the magnitude of r prime, which is x prime of t squared plus y prime of t squared plus z prime of t squared. It shouldn't be necessary. I don't think I'm going to do that anymore because it makes it too cluttered here. So you should be clear what we mean by f of r of t times magnitude of r prime, because right now we should be familiar with these notations anyway. Okay, so let's get straight to the example. Go slow, especially when you set up. Sometimes it takes a while because often the parameterization is not given, so you have to come up with it yourself. So let's start with a two-dimensional example. Let's say I have to compute the integral of over c of the function square root of 2x plus y ds, where c is defined as x equals 2y squared. Let's say with y between 0 and 1. Okay, so often the parameterization is not given. In other words, c is not given as a vector function. In that case, you have to come up with one. Now, you have to be careful here. For example, if you have a circle or a portion of a circle, the parameterization that might work most of the time better is given in terms of polar coordinates. If there is no obvious smarter way to come up with a parameterization, typically you're going to choose one of x or y or z in general to be the parameter t. And you have to choose it in such a way that it makes computation easier. So for example, it doesn't make sense to make x to be t, because then you're going to have y in terms of square root of t over 2 or something. It's easier to think of, in this case, to choose y to be t. So of course, because y is between 0 and 1, that means t is also between 0 and 1. And then going back to the equation of the curve, x is 2t squared. So by the way, the path here, the curve, is basically a piece of the portion of a parabola like that, right? So between the points 0, 0 and the points 2, 1. Right? When y is 1, x is 2. So go slow on this and then make sure you clearly write the correct parameterization for the curve that is used in the integral. So r of t in this case is going to be 2t squared, because that's the x component, followed by t with the parameter domain 0, 1. Okay, so now we have the curve in the correct format, and then we can now set up the line integral to compute. So the line integral over the function square root of 2x plus y ds is the integral from 0 to 1, and now we plug in the actual curve. So that means x is going to be 2t squared, y is going to be t, into the function to integrate. So square root of 2 times 2t squared plus y, which is t. We're going to have to multiply by the magnitude of r prime. So let's do it in two stages here. So times magnitude of r prime. Now r prime is going to be 4t and 1 dt. One step at a time. Again, pause me and go slower if you need to. The computation is not hard here, but just make sure you understand each single step. And now magnitude of 4t1 as a vector, that's going to be square root of 16t squared plus 1 dt. Okay, let's simplify this a little bit. Square root of 4t squared, that's going to be 2t because it's positive. So this is 2t plus another t, that makes it 3t. And the way it looks, it's suitable for a u substitution. We can choose u to be 16t squared plus 1. That makes du 32t dt. And the new bounds of integrations, if t equals 0, u equals 1. If t equals 1, u equals 17. Moving on, the new integral now is from 1 to 17. 3 is a constant. Square root of u is like u to the 1/2. And then t dt from the substitution is du over 32. So we have 3 over 32 outside. Integrate u, which is 2/3 u to the 3/2 between 1 and 17. Some cancellations there. And that makes it 1 over 16. And then plug in the bounds, 17 to 3/2 minus 1 to the 3/2. Okay, so most people, like I said, have troubles actually getting confused on the setup. The setup of these integrals in the last chapter are a little bit more involved. The reason is because the domain itself is not just an interval. I mean, it's not just, you have to do some work on the domain. Just like, for example, when you did the recalculation of the bounds for multiple integrals, like double or triple integral. Here we have to carefully choose the parameterization if it's not already given, and then especially make sure we plug it in correctly. Don't confuse, of course, the scalar with vectors and so on and so forth. So let's go about other examples. Now, let's do, the next two examples are very important to understand, not just for the sake of computation of the line integral, but for the for a connection with the next topic. But actually, before I do those important examples, let's actually do another simple one with a function of 3 variables. So second example, and I think this one fits in this page, hopefully. So let's say I have to integrate the function x squared plus y squared plus z ds. And here the domain of integration, the curve, let's say it's given already in the parameterization form, parametric form. Let's say it's cosine of t, sine of t, and t. Again, with the domain between 0 and 1 for t. Here the parameterization is already given, so we can just go straight away to the actual integral. So from 0 to 1, plug in the curve components carefully. So the components plugged in into x, y, z. So that means x squared becomes cosine squared t plus y squared is sine squared t plus t. Arc length is the magnitude of r prime. So r prime is minus sine of t, y prime cosine of t, z prime is 1. And obviously be aware of simplifications along the way. Cosine squared plus sine squared is 1, so over there we have actually 1 plus t. And the magnitude of the r prime happens to be a constant via the same simplification, right? Sine squared plus cosine squared is 1. So we're left with actually 1 plus 1, which is square root of 2, 1 plus t. We can pull root 2 out and then integrate between 0 and 1. So if you plug in 1, that's root 2, 1 plus 1 over 2. So that's 3 over 2, 3 square root of 2 over 2. All right, so that was another example. And then let's do 2 more side by side. It's going to be the same function, but over 2 different curves. And again, we're going to make a remark on that, which is quite important, like I said, for later topics of this chapter. So stay tuned for the next page. Okay, so let's look at the following example. Suppose we have 2 curves. And again, for simplicity, we're going to focus on 2-dimensional curves, although what I'm going to talk about in these 2 examples holds for 3-dimensional curves as well. And I'm gonna tell immediately how these are defined. But the goal, for example, let's choose a function here, f of x y equals x squared plus y. And I'm going to compute in this page the integral of the same function, but over two different curves that start and end at the same point. In this case, -1, 0, and 2, 3. So more to the point, the first curve is a line. You can actually compute the equation of that line if I give you the 2 points, but let's just give it already. So the first curve is r of t given in the parametric form by the segment 3t minus 1 and 3t. And then the domain is going to be, again, 0 and 1. Is the easiest domain to work with because it makes the computation easier. So if you look carefully, if I plug in 0, I get the point -1, 0, the initial point. And if I plug in 1, that's 3 minus 1, 2, and then 3. So that's C1. And then C2 is going to be a portion of a parabola, which in the parametric form is given by t and t squared minus 1. This time with the domain given by -1 and 2. Again, let's check carefully here. If t equals -1, I get -1 and 0, -1 squared plus -1, right? So that checks. And then if t equals 2, I get again the same final point, 2 and 3. So again, convince yourself that the actual point, not the parameters, by the way, the parameter values are not the same, obviously, but the actual point on the curve is the same, the initial and the final one for both of them. So to be clear, it's same endpoints, but different curves, different paths from one point to another. So let's compute the two line integrals. So we're going to start with the first one. So the integral over C1 of f of x y ds. Parameter domain in this case is 0, 1. Let's plug in the curve. So we have 3t minus 1 squared plus 3t. And then the arc length, magnitude of the tangent, r prime is 3 and 3. So we're going to have the magnitude of that, ds. So let's expand this quantity here. We have 9t squared minus 6t plus 1 plus 3t, and then square root of 9 plus 9 dt. So this is dt. So we have 9t squared minus 6t plus 3t, that's minus 3t plus 1. Square root of 18, that makes it like 3 root 2. We can pull that constant out and then integrate. 9t third over 3 minus 3t squared over 2 plus t between 0 and 1. So let's see what we get. 3 root 2, plug in 1, so that's 3 minus 3 over 2 plus 1 times, let's see, we're going to multiply by 2. 6 minus 3, that's 3, plus 2, that's 5 over 2, 15 over 2 over 2, which is approximately equal to 10.6. Okay, you should pause me probably and do these examples on your own and then check just for practice. Let's do the other one. Same function again. Keep in mind, same function, same initial and final points, but a different path altogether. So once again, we're going to have the parameter domain, in this case, -1 and 2. Plug in the components of the second curve into the function. So that's t squared plus y, that's t squared minus 1. Magnitude of the tangent vector, which is 1, and then 2t. 2t squared minus 1, magnitude of the unit this tangent, which is going to be 1 plus 4t squared. Okay, this is not going to be doable with classical methods. Actually, it is doable, but it's far too tedious. You're going to need actually here trig substitutions. So why don't you just plug it in into Maple or Wolfram Alpha, and then convince yourself that you're going to end up with, in this case, approximately 12.03. Okay, so what's so special about this example? Well, it'll be clearer what we talk about later in the next sections. But let's write it as an important remark here. Generally speaking, right, the line integral, if you look carefully, depends on of a function. The line integral of a function depends on endpoints, direction, right, on the path, right? I mean, we'll talk about that in a moment, because if you reverse the direction, you change the sign of the integral. Direction and the path. Okay, which is basically unlike the Riemann integral, right, which is defined of a regular Riemann integral from calculus 1, which is, you know, depends on the path or the endpoint. So let's illustrate what we're talking about in a moment here. In calculus 1, you know that the integral from a to b of a function is minus the integral of b to a of another function, right? So that means if you change the direction over the domain, from a to b versus from b to a, because if the domain is a segment, right? So if your domain is on a real axis, directions is either left or right. Okay, so you change the direction, you change basically the sign of the integral. So the integral from a to b is minus the integral from b to a of the same function. But other than that, depends on the endpoints only. Now here, because you have infinitely many paths between one point to another, the path also matters in terms of what the actual line integral is equal to. So you can also write the fact that the integral over a curve, if you, well, we're going to write that on the next page because I want to make a notation here. So if you change the order of the, if you change the direction of on the curve, you change also the sign of the integral. But again, even if the direction is the same, like in other words, if you go from point A to point B, it matters the path you take because that affects the value of integral. There are some special types of line integrals in which such direction doesn't matter. The so-called line integrals over conservative fields. So keep this in mind because, like I said, in general, the path matters for the value of the integral, with one exception which deserves its own discussion later. So let's establish that, well, let's actually talk about a couple of properties before we move on. If you, let's say you have a curve that you traverse from A to B. If you decide to traverse it backward, remember minus C is a typical notation of the curve traversed from B to A. So just like in the Riemann integral from calculus 1, it is true that the line integral over a curve traversed from in one direction is minus the integral over the same curve traversed in the opposite direction. That's very easy to realize because it's the Riemann sum. You change essentially the sign of the you change the sign of those terms in the Riemann sum. So that's analogous to saying that the integral from A to B is minus the integral from B to A. So that's what we mean by the fact that the direction matters when you compute the line integral. Okay, so let's move on the next page to define now the second type of line integral, namely the line integral over vector fields. Okay, so here's the default example that I like to give to introduce the this different type of line integral. So this time, again, the domain of integration is going to be still a curve. So the main ingredient is still a curve given by r of t, but what you're going to integrate is a vector field in 2 dimension or 3 dimension. Remember, by that we mean this time a vector, right? So, you know, when we say, for example, f of xy, that's going to be basically a vector, right? So, I mean, at each point you have, you know, for example, f of xy is given usually by some function at xy for the first component, another function of xy for the second component, and then similarly for a vector field in 3D. So the default example is the following. Let's say we have what is called a force field. Okay, so I'm not going to do lots of sketching here or writing down. Just hear me out when I describe what you should imagine here. A force field meaning that at each point in the space, let's focus on the 2-dimensional space. At each point, you have a force acting on that point in various directions, right? And let's say you have a path C in the force field. Okay, so you have this path given by C, and again imagine that at all points you have these forces acting on those points, right? Wherever you are in this field, and that force field again is given by the vector field f of xy. And you have this path, and then you have an object moving on this path, along this path. So let's say the object is over here at this point. And let's say right at this point, the force field acts this way. So this is big F acting on that point. One question you can ask in this configuration is, what is the work exerted by the force field in moving the object along this path? Okay, and the work, remember, can be a positive or a negative contribution, because as you move along this path, some components, the component of the force field that is along the motion can help or hinder the motion if it's in the direction of the motion as opposed to opposite the direction of the motion. Let's say the motion is in this way, right? I put the arrow here. So how do you compute the work? Well, the work, remember, is essentially the dot product, or in other words, the component along the motion, along the motion of the object, the component of the force times the distance traveled around near that point. So again, this leads to an integral, because imagine you split the path again into small equal pieces, and you want to compute the work just near that tiny little piece. You sum up the work at these pieces, and that results into a Riemann sum, right? And then when you actually compute that Riemann sum and take the limit, you're going to obtain an integral which in this configuration is going to represent the work exerted by this force field in moving that particle. Okay, so more to the point, let's say, let me see if I can do this with a different color here. Actually, let's I think we'll do that with a different color. So let's say right at this point, the motion, the direction is given by the unit tangent. Remember, the unit tangent is the default way of indicating the direction of motion. So t is the unit tangent. Let's denote by ds, as always, the arc length. If you partition this curve, so that's ds. And let's denote by theta the angle between the force field and the unit tangent. Okay, so if we project F, right, so let's actually do this picture over here one more time. So you have the arc length. I'm going to exaggerate a little bit the distances there. You have the unit tangent, you have the force field here. The component and theta, right? The component that participates in the work is going to be perpendicular to the unit tangent. So what you're actually going to integrate is going to be the magnitude of the force cosine of theta, because that's the component along the unit tangent, and then multiplied by ds, the arc length. Okay, but let's actually, recalculate this in a different way, or write them in a different way. Notice that cosine of theta, if you remember the formulas for the angle between two vectors, that's actually the dot product between f and the unit tangent divided by the magnitude of f and the magnitude of the unit tangent. What about the arc length? Well, the arc length is nothing but we'll get to that later. So let's still keep it ds. All right. So the magnitude of that cancels, since we have the unit tangent here. The magnitude of the unit tangent is obviously 1. So it turns out that what you integrate when you come up with this integral is actually the dot product between the force field and the unit tangent times the arc length ds. So this is the reason why the formal notation looks like this. Now, when we actually evaluate this on the curve, right, when you actually plug in the components of the curve C of t, we can still write this in a slightly different way. So let's actually come up with another way of writing this. So the force field, again, evaluated at the actual curve is going to be f of r of t. That's the moment when you actually plug in the components on the curve. And the unit tangent, remember, is going to be r prime of t divided by the magnitude of r prime of t. And ds, remember, is the magnitude of r prime of t, which is a scalar, okay? So again, keep in mind here, this is a scalar product on the outside of this parenthesis. You can bring this scalar inside the parenthesis, which means it will cancel, and this dt, obviously, right, when it comes time to integrate. So the stuff to integrate when you evaluate the whole thing on the curve is nothing but the force field or the vector field evaluated at the curve dot r prime of t, and then dt. And so this indicates the way to set up the line integral over a vector field in a computational form. This again will be the formal notation. There are actually two notations that you can think about. We can put them in the formula sheet, and then at the end of this row is the way to compute it. So let's write it down, and we're going to write it on the next page as well to have it in front of us. The line integral over vector fields, the formal notation is going to be big F dot t ds. Another formal notation that is quite practical is f bar dot dr. This is again a shortcut to indicate that you basically do the dot product of the vector field evaluated at the curve dot the derivative of the vector field. dr, think of it as like the differential of r, right? Which is the derivative of r dt, basically. So again, it's important to keep in mind these are just formal notations. And then the way to compute it comes at the end. Again, the parameter domain for the curve, right? At the beginning here, between a and b. The vector field evaluated at the curve dot r prime of t dt. So remember, this is the dot product, not the regular product. So let's move on the second page on the next page with a couple of with one example and some remarks, and I think that'll. Okay, so let's do an example. So suppose we want to integrate the vector field given by the component xy, right? So notice that even though this depends on x, y, and z, it doesn't have to depend explicitly on z. So any components will do. I mean, like, it doesn't have to be, although it's in 3 dimensions, you don't have to have z. It can be even a constant, right, the vector field. Although it won't be interesting for our purposes, right? And then the curve is given by r of t with the components cosine of t, sine of t, and then t, with t between, let's say, 0 and pi. So here you have to go slow actually with setting it up. We're going to talk about that in a moment with a different example, but which we will only set it up just to see how it works. And so let's see. So we want the integral of over c of f dot t ds, and again, like I said, you could also write it like that, f dot dr. So as the name implies, this is basically the integral from a parameter domain from 0 to pi, f of r of t dot r prime of t. Most people actually have troubles here. I mean, those who have problems or troubles, they get confused with the setup and the substitution here. So into the vector field, you're going to replace x, y, and z with the components on the curve. It's just like the line integral over scalar fields, but here you have more substitutions to me. I mean, not more, but just look at carefully at these components. So the first vector, f of r of t, becomes x is replaced by cosine of t, y by sine of t, and then x times y by, obviously, cosine of t, sine of t. Okay, so that is f of r of t. Then you're going to dot this dot product with r prime of t, which is minus sine of t, cosine of t, and 1. T prime is 1. Now do the dot product and simplify. So cosine of t times minus sine of t plus sine of t times cosine of t, and then finally plus cosine of t sine of t times 1. Here we have a simplification, so this ends up being the integral from 0 to pi sine of t cosine of t dt. This works with a u substitution for sine. New bounds are sine of 0. I'm sorry, let's use the domain 0 pi over 2, because otherwise it's trivial. So let's say the domain is 0 pi over 2. So the new bounds are sine of 0, 0, sine of pi over 2 is 1, u du. So that's 1/2 u squared between 0 and 1, which is 1/2. So just to set up another one, to see how it works. So let's say you have big F of x, y, z given by, you know, x plus z, y plus z, let's say x times y, and then the curve is given by t, I don't know, t squared and t to the power 3. We're not going to compute this because it's probably impossible to compute, but so let's say t between 0 and 1. So that's the curve C. So again, when you set it up, carefully plug in the components of the curve for x, y, and z. Carefully, right? So x plus z is just t plus t third. Y plus z is t squared plus t third. X times y is t times t squared. And then dot r prime, which in this case is 1, 2t, 3t squared dt. And obviously make sure you do the dot product first. T plus t third times 1, t squared plus t third times 2t, and then plus t times t squared, that's t third, times 3t squared, and the whole thing becomes a Riemann integral dt. We're not going to compute this because although it's not overly, I mean, it's not totally impossible, because I just wanted to focus on the actual setup. One last remark. Make sure you know the interpretation of the curve, right, of the line integral over vector field. Another interpretation, for example, with fluid dynamics is that a line integral over vector field represents the circulation along this path C. So if you imagine that F denotes, for example, a velocity field in a fluid in space, then this curve measures actually how much of that fluid flows along the curve. The actual sign of the integral can also be inferred if it's along the motion or against the motion. So let me make a point like this. So for example, let's say this is the path, and let's say the force field looks like that. Okay, so it's pretty obvious in this case that the actual line integral over this path is going to be positive, because the components of F along the path, so again, assuming the path is this way along the curve, right, from left to right. Let me make that in actual red color here. Right, so let's say you traverse this from left to right. The components of F along C, along the path, are in the same direction of motion on C. So if it's a force field, in other words, each force helps the motion. It's in the direction of motion. And obviously, if I traverse the curve in the opposite direction, then the line integral will be negative. Now, obviously, most of the time you won't be able to tell if the arrows are all over the place, right? If I have like that, right? You will have to actually compute the integral to infer whether the integral is positive or negative. So I think that's it for today. We'll continue next time with the next topic.